Let us move on to example 2.12. A runoff river hydroelectric plant with pondage has the following data. Installed capacity of the plant is 10 megawatts. Water head is available at 20 meters. Overall efficiency of the plant is 80% and load factor is 40%. You have to determine the river discharge in meter cube per second required for the plant. So you have to calculate how much discharge of water must be available every second, how much volume of water must be displaced every second from the dam to ensure, or in the river, to ensure that 10 megawatts of power is generated. So consider that we have 1 week of duration. So units generated per week will be maximum demand into load factor, which will be the average load into number of hours in a week. So the total number of units that will be generated in 1 week will be 67.2 into 10 power 4 kilowatt hours. If Q is the discharge in meter cube per second, which is required to generate this much amount, these number of units, then weight of water available every second will be the discharge in meter cube per second into density in kilogram per meter cube into the gravitational force, which gives you 9810 q newtons. So the average power produced will be the weight of the water into the height of the head into the overall efficiency. That gives you 9810 q into 20 into zero point 0.8. That gives you 156,960 q watts or 156.96 q kilowatts. So units generated for per week with this much kilowatt power will be 156.96 q into the total number of hours in a week. That will give you 26,369 kilowatt hours. But we already know that units generated per week with our power is 67.2 into 10 power 4 kilowatt hours. So we compare these two, and by comparing these two we get the average discharge required for this plant to generate this much power as 67.2 into 10 power 4 divided by 26396. So 25.48 meter cube per second must be displaced from to produce this much amount of power, 10 megawatts of power. So if the river discharge, if on a particular day the river flow is 20 meter cube per second. So now the river on a particular day the river flow is not 25.48 meter cube per second, but now it is 20 meter cube per second. What will be the load factor that the plant can supply? Obviously, if the discharge has reduced, then the load factor which the same plant can supply is also reduced. So let us see how much it is reduced. So if the river discharge on a certain day is 20 meter cube per second, then the power developed during that time is 156.96. This is the power which we found. This much kilowatt of power will be generated. Average power will be produced. So if on a particular day Q is 20 meter cube per second, we simply put it here and we find out how much power is generated. So that is 3139.2 kilowatts. So units generated on that particular day will be the power which will be generated during that day and into the number of hours in that day, which is 24. That will give you 75,341 kilowatt hours units will be generated in that day. So the load factor will be the maximum demand, which is 10 raised power 3. 10 megawatt is 10 into 10 power 3 kilowatts. So 10 power 4 kilowatts into the 24 hours will be divided by will divide this 75,341. So that gives you 31.4%. So the load factor on that way will be 31.4% rather than 40%. As we have described previously, the load factor will fall. Now let us move to the final example related to hydroelectric power station, which is given in your textbook. So over here you are given the load curve. So load curve is or in this case this is not a load curve, this is the weekly discharge of a typical plant. So you can see that the number of days of the week are written on this axis, and then the discharge on any given day in meter cube per second is given by this graph. So average discharge can be found and is represented by this dotted line. So on Sunday the discharge is 500 meter cube per second or Qmax. On Monday it is 520 Qmax. On Tuesday it is 850 Qmax. On Wednesday it is 800 Qmax. On Thursday it is 875 Qmax. Friday 900 Qmax and Saturday 546 Qmax. So the plant has an effective head of 15 meters. Effective head of the plant is 15 meters and overall efficiency of plant is 85%. If the plant operates at 45% load factor, estimate the average daily discharge. You have to tell how much water must be discharged on average daily. The pondage required, how much what is the size of the pond that is required to ensure this average daily discharge, and the installed capacity of the proposed plant. So let us move to find the solutions to all of these things. So first of all, let us talk about average daily discharge. So figure 2.5 shows the plot of weekly discharge, and this graph discharge is taken along the y-axis and raised along the x-axis, as I've told you previously. So average daily discharge is simply you add up all of these discharges and divide it by 7 days in a week. So you get 713 meter cube per second, which is the average daily discharge. So it is clear from the graph that on 3 days, like Sunday, Monday, and Saturday, the discharge is less than the average discharge. So the discharge on Saturday, Sunday, and Monday is less than this average discharge. So on these days you will need to provide water from storage. So the volume of water actually available on these days is, the volume of water available on these days is 500 into 500 is available on meter cubes are available on per second are available on Sunday, Monday 520, and Saturday 546. So into the total number of hours in that day, into the total number of seconds in 1 hour, you will get the volume of the water available, aggregated volume of water available in these 3 days. So that gives you 1566 into 24 into 3600 meter cubes. So volume of water required on these days is average discharge multiplied by 24 multiplied by 3600. So on these 3 days, the and multiplied by 3 because of the 3 days. So 3 into 24 into 3600 into 713 gives you 2139 into 24 into 3600 meter cube. So this is the volume which is required in these days to produce power at average discharge rate. So pondage required is the difference of these two. So the volume which is required is given here, the volume which is available is given here. The remaining water needs to be stored for these 3 days to make up for the loss in power. So 2139 minus 1566, and the remaining is obviously common to both. So you get 495 into 10 power 5 meter cube. This is the pondage, the volume of water which needs to be stored inside the pondage which you create. So the weight, finally we find out what is the installed capacity of proposed plants. So with this pondage, the weight of the water available every second, when you create this pondage, you will have the average water discharge rate which is available on all the days, which is 713 meter cube per second. So with this discharge rate, on average discharge rate, you can calculate the weight of the water that is available to you on average, that every second. So 713 into density of water, which is in kilograms per meter cube, and into 9.8, which is the acceleration due to gravity. So this much weight of the water is available to you on average in this week. So average power produced per week is weight of the water into height into overall efficiency, weight of the water into height into overall efficiency. That gives you 89180 into 10 to the power 3 watts, or 89180 kilowatts. So the installed capacity of the plant must be able to meet the maximum demand. Maximum demand you can find out by using this average power and dividing it by a load factor. So the maximum demand which will occur on this power station will be 223 into 10 to the power 3 kilowatts, or 223 megawatt. So the capacity of this plant in order to handle this maximum demand should be 223 megawatts. So you should make this plant and the total number of generation units which you install inside this plant, their ratings should equal, should aggregate to 223 megawatts. So this was all about examples related to application of knowledge about hydroelectric power stations, and typically we in these examples we have seen that how to create pondage to ensure average discharge is available from hydroelectric power station to create a constant uniform power throughout a given time period. So let's move on So here is your exercise number 2. You have to attempt all the tutorial problems on page 27 of the soft copy of your textbook, which is available to you from shared OneDrive link, which I have shared with you. So on page 27, there are some tutorial problems after the final example of hydroelectric power station, and you have to attempt all of these tutorial problems. And I recommend that you attempt all of these tutorial problems and see if there are some problems which have some data missing or they cannot be solved, and bring them to my attention so that I can give you the data and you can solve those problems. And that is all for as far as hydroelectric power stations are concerned. So in the next week we will be starting from the diesel electric power stations. Take care. Allah Hafiz.